welcome to the SOLEIL Infrared Learning Series. This episode, Ep38 Synchrotron Infrared Light Source, Ultra Bright, Ultra Resolution. Then close with the checklist. Next on you, using a light factory to see a cell. In 2010, Michael C. Martin of Lawrence Berkeley National Laboratory, LBNL, and Paul Dumas of SOLEIL Synchrotron in France, wrote in a review in Comptes Rendus Physique. Synchrotron infrared light is 1,000 times brighter than a conventional thermal source. This brightness advantage, when coupled with an STIR microscope, allows diffraction-limited microspectroscopy at unprecedented signal-to-noise ratio, making it possible to acquire high-quality spectra from a single living cell, a single polymer microdomain, or a single catalyst particle. Latin MC UMRP. Next, Synchrotron radiation, superlight from relativistic electrons. 1.1 Physical origin of synchrotron radiation. Synchrotron radiation, SR, is electromagnetic radiation emitted when charged particles move in a circular path at speeds close to the speed of light under magnetic fields. Its physical nature can be described by classical electrodynamics. Next, SNR improvement from theory to practice. 2.1 Analysis of SNR sources. The SNR occurs mainly affected by the following factors. Next, spatial resolution, approaching but not breaking the diffraction limit. 3.1 Synchrotron radiation cannot break the diffraction limit. Recall from Ep36, spatial resolution is constrained by the Hebbe diffraction limit d approximately equals 0.61 lambda. Synchrotron radiation cannot break this limit. Diffraction is a universal property of waves independent of source brightness. Next, major synchrotron infrared beamlines worldwide. 4.13 generations of sources and infrared beamlines. Synchrotron radiation sources are typically classified by generation OCP. Next, V-Draper-Phase Case 1, single-cell imaging. 5.1 Why do single cells need synchrotron radiation? A single mammalian cell is about 10-20 m in diameter, comparable to the diffraction limit at 1,000 centimeters. This means, next, Vice-Precious Case 2, nanomaterial characterization. 6.1 Infrared challenges for nanomaterials. Nanomaterials, e.g., nanowires, quantum dots. 2D materials typically have characteristic sizes 1 m, far below the infrared diffraction limit. Conventional fur cannot directly image individual nanostructures. Next, frontiers of synchrotron infrared. 7.1 Synchrotron plus FSPA high-throughput chemical imaging, combining a synchrotron high-brightness source with an SPEC array is a recent trend in trend. PAPA requires uniform illumination, but the synchrotron beam is small and Gaussian distributed. Solution: an annulator instead of a bending magnet to provide more uniform high-brightness light. An SLC voice beamline has achieved synchrotron plus 128 times 128 f-SPEC, covering 200 times 200 micrometers per frame, SNR 1000 E. Next, limitations and challenges of synchrotron infrared. Cannot break the diffraction limits. Still constrained to unequal micrometers at 1,000 centimeters. Submicron imaging requires exposure or FMIR scarce beam time. Competitive application process may wait 6 to 12 months from proposal to experiment. Sample transport. Biological samples require cryogenic transport. Some samples, which volatile, are difficult to adapt to the beamline environment. Virus stability. Beam decay requires periodic top-up. Top-up mode can mitigate data volume. High-resolution imaging generates GB-level data, requiring beamline computation support. High cost. Building a third-generation light source costs $1B. Annual operation inferred $100 million, requiring national investment. 8.2 Relationship with X-Current and off-mirror. Next, Thought questions. Synchrotron infrared brightness is 101,000 times higher than low bar, but spatial resolution cannot break the diffraction. Please explain physically what does brightness improvement. You need to study the lipid distribution, 1,740 centimeters of a single live cancer cell, 15 micrometers diameter. Please calculate the theoretical diffraction limit of globar and synchrotron radiation at this wavelength, and explain why GLAR's actual resolution in this application is far below the diffraction limit. Finally, the drill actualists, make sure you can recall each item. Core knowledge point. Key points. Definition of synchrotron radiation. Electromagnetic radiation emitted when relativistic electrons move in a circular path in a magnetic field. Four main characteristics of synchrotron infrared. High brightness, 101,000 times GLAR broad spectrum. High collimation boost structure, SNR improvement. Can 100 times globar under small aperture, 100 times under 3 micrometers aperture. Spatial resolution. Approaches but does not break the diffraction limit, 3 micrometers at 3,000 centimeters, 10 micrometers at 1,000 centimeters. High wavenumber advantage. High wavenumber, short wavelengths naturally has better diffraction limits commonly used for single-cell imaging. Major beamlines. SOLEIL Els1.4.4 SSRFBL01BNSLCO RMI. In-time application. Proposal-based. Free. Highly competitive. Must clarify why synchrotron is necessary. Single-cell imaging. Hemoglobin distribution in red blood cells. Abnormal nucleus to cytoplasm ratio in cancer cells. Plant cell wall components. Nanomaterial characterization. Carbon nano-2 GD ratio. Catalyst co-adsorption. Low wavenumber vibrations of 2D materials. Quantia directions. SR plus FSP, SR plus R3, SRT Murray's alt, SR5 rear. The main limitations. Cannot break diffraction, scarce beam time, high cost. Competing technologies. Up-tier, submicron, FMIR, nanoscale, encroaching on low resolution market. That covers the required sample for this episode. Practice with real spectra on ftir.fun and continue with the next lesson.